Did you know that we can create diamonds out of thin air? This idea might seem like something out of wizards' novels, but in reality, it is something that can effectively be achieved through chemistry. To understand how it's possible to create diamonds from thin air, we first need to understand what is a diamond. Diamond is defined as a solid form of the element carbon with its atoms arranged in a crystal structure called diamond cubic. So basically, a diamond is a crystal which consists of a group of carbon atoms that are arranged in a cubic structure. Now you might be asking, how is it possible to create diamonds from thin air? Well, to understand how it's possible, you need to first know the composition of air. Air consists of 78% nitrogen and 21% oxygen, and small amounts of other gases too, such as carbon dioxide, neon, and hydrogen. The percentage of carbon dioxide in air is about 0.04%. A carbon dioxide molecule consists of one carbon atom attached to two oxygen atoms. This means that carbon dioxide can be used as a source of carbon, which can then be used to create diamonds. Now you might be wondering, how can we get pure carbon from carbon dioxide? First, we can get a large amount of carbon dioxide from air through separating the carbon dioxide from other air components. We can do this by using adsorbing agents to adsorb carbon dioxide from air. After obtaining a good amount of carbon dioxide, it can be turned into pure carbon through an electrochemical process. In recent years, researchers have discovered a number of solid metal catalysts that have the ability to convert carbon dioxide into solid carbon. A catalyst is a compound that speeds up a chemical reaction. But the solid metal catalysts they discovered work only above 600 degrees Celsius. However, recently chemists at RMIT University in Melbourne, Australia developed an electrochemical technique based on liquid metals that can convert carbon dioxide to storable solid carbon at room temperature. The reduction of carbon dioxide to solid products is challenging, due to the fact that any product can cover the catalyst's surface through adhesion, which blocks access to the catalytically active sites and causes damage to the catalyst in a process known as coking. However, liquid metal-based catalysts have been shown to be extremely resistant towards deactivation via coking. The liquid nature of the catalyst prohibits the produced carbonaceous materials from adhering to the surface of the catalyst during the reaction. Gallium-based alloys are ideal for the design of liquid metal-based electrocatalysts, since they remain liquid at room temperature and are capable of dissolving most other metallic elements at concentrations suitable for catalysis. When liquid metal is alloyed with multiple metallic elements, the interfacial oxide of the liquid metal is dominated by the oxide that provides the greatest reduction in Gibbs free energy. This phenomenon can be exploited to produce highly active electrocatalysts for the reduction of CO2. In the study which was done using liquid metal for the reduction of carbon dioxide, cerium-containing liquid metals were utilized as an electrocatalytic system, successfully converting CO2 to carbonaceous and graphitic products at room temperature. The electrochemical reduction of carbon dioxide using a liquid metal catalyst was conducted in a dimethylformamide-based electrolyte, because carbon dioxide is highly soluble in the solvent. The surface of the liquid metal cerium catalyst was initially dominated by Ce2O3 at room temperature. When a sufficiently negative electrochemical potential was applied, a portion of the Ce2O3 on the surface reduced to elemental cerium. During electrocatalysis, the zero-valent cerium atoms, which were produced, were capable of reacting with carbon dioxide in a 4-electron process, leading to the formation of CeO2 and carbonaceous products. Due to the applied reductive potential, the CeO2 was continuously reduced back to elemental cerium, which drove the catalytic process. The process can be described by the following chemical reactions. The reactions from 1 to 4 are proposed to occur at the working electrode, while reaction 5 is the oxygen evolution reaction at the counter electrode. The method for the reaction was simple. First, to create cerium-containing catalytic mixture, cerium powder was added to gallium inside a nitrogen gas glove box. Gallium is an alloy composed of gallium, indium, and tin which melts at -19 degrees Celsius, and therefore is liquid at room temperature. The mixture was ground using a mortar and pestle until the alloy developed a smooth, reflective appearance, which indicated a complete dissolution of the added cerium. Second, the electrode was prepared by inserting conductive carbon fibers in a glass capillary tube with 1/2 centimeter of the carbon fiber sticking out of the capillary. The fiber was then inserted into the liquid metal cerium alloy, and through moving the capillary tube inside the liquid melt, a droplet of the liquid metal cerium was attached to the carbon fiber at the end of the capillary tube. The top end of the capillary tube was then connected to an electrochemical workstation using copper tape. Finally, the inlet of the electrochemical cells was connected to a CO2 gas cylinder. CO2 was purged with a high flow rate into the electrolyte for 30 minutes before the experiment was performed. During the experiment, CO2 was purged either at a slow rate into the electrolyte or into the headspace of the electrochemical cell. By the end of the experiment, the carbon dioxide was converted to carbonaceous material. After the carbon dioxide is converted to pure carbon, the pure carbon can be used to create diamonds. Now, of course, your next question is, but how can we do that? The fact is, there are two ways which can convert carbon into diamonds. These methods are chemical vapor deposition and high-pressure, high-temperature synthesis. In the chemical vapor deposition process, a material is placed in a chamber in the presence of a pure carbon plasma. As soon as the process starts, the carbon atoms start getting deposited on the material, and with time they form a man-made diamond. In the process, the chamber is filled with carbon material. Then the chamber is heated to about 900 to 1200 degrees Celsius, and the solid carbon is etched using a hydrogen plasma. After that, a microwave beam causes carbon to precipitate and deposit out of a plasma cloud and onto a seed crystal. Finally, after the process ends, the synthetic diamond crystals are removed and ready to be cut and polished into the final product. In the high-pressure, high-temperature diamond growth process, the growth takes place in a small capsule inside an apparatus which is capable of generating very high pressures. Within the capsule, a carbon starting material, such as graphite, dissolves in a flux of molten metals such as iron, nickel or cobalt, which lowers the temperature and pressure needed for diamond growth. The carbon material then migrates through the flux towards the cooler diamond seed and crystallizes on it to form a synthetic diamond crystal. During the process, a diamond seed is placed in a designed press. The chamber is then heated to 1300 to 1600 degrees C with pressures above 870,000 pounds per square inch. The molten metal dissolves the carbon source. Then the carbon atoms precipitate on a small diamond seed crystal, and the synthetic diamond begins to grow. Finally, the lab-grown crystal is cut and polished by a diamond cutter. You can clearly see that through multiple processes together we can use the carbon dioxide in the air to create diamonds. However, doing so is expensive, and isn't really a lucrative way to produce diamonds. And there are more effective methods for reducing the carbon dioxide percentage in the air. Thank you so much for watching the video, and we hope you found it informative.